All right, let's have a look here. So just a little bit of review from a few sections ago. How could we easily, what are our options here? How can I evaluate that function at 2? Say it again. Plug in 2, I'd plug in 2 for x, that would work. Yeah. It's, in this case, it's not very hard to do. But what if I had, really big powers and big numbers that I'm evaluating that? Then that might be kind of rough, right? So what's my other option we got? Remember?
You just do it like y equals the top of x. Isn't something synthetic division?
Okay, yeah, we could use synthetic division, right? There's kind of a fringe benefit of synthetic division. So we could set up our template. Okay, what goes where? Good, 2 goes out front. Good. What goes up here? Good. Okay. And what's significant about the remainder box? Yeah, thank you. Yeah. What's significant about, we haven't done anything yet, but what's significant about that remainder box? It's a little crooked, it is.
It's the same color as the line.
Well, when we get there, you can tell me. So now what do I do? Okay, bring the 1 down.
Oh, that would be good.
Now what?
Multiply by 1.
Okay, 2 times 1 is 2. That goes there. 0, I add them, so I get 0. Okay, what's significant about that? That's the answer, isn't it? Right? So if I were to write this whole thing out, what do I get? I'm going to end up getting, because I'm going to end up getting that, aren't I? Right? So here's my 1x squared plus 0x minus 5. And here's my plus, my negative 4 is what is the remainder. Okay, but it's also the value of the function. Right? So we have that coincidence. Not really coincidence. We're going to find out that it's that way for a reason. But that really helps us out. It's an easy way to evaluate a function. Okay? So that reminds us about what's called the remainder theorem. I don't know if we called it that at the time, but now we are. So if a polynomial f of x is divided by x minus k, then the remainder is the value f of k. It's always that way. So the remainder, when we divide the polynomial out, we divide it by x minus k. The remainder is the value of the function at the 0 of the denominator, right? That's being subtracted from x. Okay. So hopefully that's what we're plugging into the function. Okay, so then how could we put that to use? Question? You want to see that some more? I'm going to put these on my notes, so they'll be there. Okay. Okay?
Yeah.
All right. So here's our picture then, right? Okay, so we know that this has got the value of the function at 2 is negative 4. Okay, when we divide it all out. So what about this one? We're going to find all the real zeros of x cubed minus 125. Just a little review of stuff we're doing now. What would we do there? We're going to find all the zeros. What's it mean when I talk about zeros? What are zeros again? Zeros of a function? Okay, where it crosses the x-axis, where the function equals 0, right? So we're just going to set the function equal to 0 and solve. We're finding zeros. So how do I solve that one? Okay, now, yeah, I mean, we haven't talked about that yet, but if I'm finding real zeros, I could isolate x, but we haven't gotten there yet. That's coming up. For now, what do we do? Difference of cubes. Okay, we write it as x cubed minus 5 cubed, right? And then that's a pattern, right? So what's the pattern? So I'm going to get it's going to factor into the quantity x minus 5 times plus 5x plus 25. Good. Okay. And then now I could just apply the zero product property, right? Set those equal to 0. And I get x equals 5. What's going to happen if I set that equal to 0? Nice. Good. I'm getting a complex conjugate pair of zeros that are non-real. So if I'm looking for the real zeros, I don't even have to worry about that one, do I? Right? So if we want the real zeros, that's not going to give us any. We already know that. Okay? What about that one? Find a real zero of that. I'm finding zeros. What do I do? Where the function equals 0.
Yeah.
So I can just set it equal to 0. And what do I get if I set it equal to 0? Yeah. We don't know what g of x is, so we can't really find any zeros of that one. But by the zero product property, this product equals 0 when either x minus k equals 0 or g of x equals 0, right? Now, where does g of x equal 0? Oops. Who knows? We don't know where g of x equals 0. We don't know what g of x is, but we know that this factor is 0 when x equals k, right? So what's the moral of that story? Okay, the factor theorem. So we just got to make this connection, and you've probably already made this connection, but here it is officially. According to the factor theorem, k is going to be a 0 of the function if and only if x minus k is a factor, right? Going back to that last example, we know that 5 is a 0 because x minus 5 is a factor, right? That makes sense? So what if, pose you another challenge here, what if we wanted to build, let's say we want to build a function out of the zeros, say we have the zeros x equals 2, x equals negative 5, and x equals 0. Those are my zeros. What's one function that would have those zeros? What do you think?
That quantity x minus 2 times quantity x plus 5 times x.
Okay, so we get x minus 2,
Or x minus 0.
x plus 5, and then just x minus 0, which we could just call x, right? I mean, minus 0 doesn't really do anything for us. Okay, so then all I'd have to do, if I want to put that in standard form, is multiply it out. But that is a function that has those zeros. Are there other functions that have them? Sure. I could multiply by x plus 11, and now I've added another 0, but it still has, where'd my x go? But it still has those other 3 zeros, right? I could multiply the whole thing by a constant out front if I wanted to, and it's going to maybe stretch it or compress it and flip it, but it's still going to have those same 3 zeros, isn't it? Yes?
Is there any problem that we will have to write a first fraction calculator as certain zeros?
Say that again?
Is there any time we'll have to do this for?
Yes. Yeah, you will.
Well, we will accept if you just add something that's already in.
Well, no, because I'm going to phrase it in the way I'm going to say, write the simplest possible function that has those zeros. Right? So the lowest degree polynomial that has those zeros. And I'll probably say something like, and assume the coefficient is 1. Right? So we don't multiply anything out front. Yeah, but there are an infinite number that have them. Okay. So then what about one like this? Here's the problem for the data. How could we do one like this? I want you to find all the real zeros of this function, and this is not an easy one to do, right? If we look at this function here, up to today, what's our only method for finding the zeros of that function? If I were to set that equal to 0, right? It'd be grouping, wouldn't it? I heard somebody say grouping. Yeah, it'd be grouping, but does grouping work? We can already kind of see, if you've done some of the grouping problems, you can kind of get a feel for the patterns pretty quick. Is grouping going to work? If I take the first group of 2, and I factor out an x squared, I get an x minus 2. Is there any way I'm going to get an x minus 2 out of the other group? No chance, right? So grouping is not going to work there. So you're out of luck. But I gave you an important hint here. I told you here's a picture of the graph of that function. Now, I didn't give you the whole, if I'd given you the whole picture, it would have been pretty easy probably, right? But I didn't. I gave you just a snapshot. So you got to do a little detective work here. How are we going to come up with the total, find all the zeros based on that picture?
Synthetically.
Okay, probably we're going to maybe use some of that, but how?
Not one.
Okay, what's 1 0?
One.
Ah, okay, so we do have a 0 here at 1, right? So we know, f of 1 is 0, right? Okay, how does that help us?
That means we know that if you put 1 in there, it's 0.
True.
Correct.
It's very true. How does that help us?
Well, does that have to do with the gravel and the opposite?
No.
Could help.
A lot of, okay.
Would you want to do something more, get that in the same exact thing?
Zeros.
Okay, I'll give you like an easier
Yes.
example to lead you into this. What if I told you, let's say we have, that's it here, make this up real quick. So, okay. So, say we start off with the number 231 sevenths. 231 sevenths, and I'm going to tell you, I want you to, I've got 3 specific factors in mind for this. Okay, now I'm going to tell you that one fractional factor of this, it's just a fractional factor, is 3, let's say is 3 sevenths. Okay, I'm telling you that this is a product of 3 numbers. And the 3 numbers are going to be 1 fraction and 2 integers. And I'm telling you that the fraction is 3 sevenths. Can you find the other ones?
Probably, yeah.
About 228, and you
Divide that first one by 3 7.
I could divide it by 3 sevenths, couldn't I? Because if I'm going to say this whole thing, let's call it P for product. Right? If P equals that, then P is going to equal 3 sevenths times something else, right? Well, let's call it, q. Right? And I just need to know what q is, because q is going to be the product of two integers, and I probably can figure that one out pretty easily. Right? So if I were to divide both sides through by 3/7, those will cancel, and I'll figure out what q is. Right? That make sense? Okay, so let's do that. So 231/7 divided by 3/7. How do we divide by a fraction?
Multiply by its inverse reciprocal.
Multiply by the reciprocal. Okay, so the 7's cancel. 231/3 is what?
117. No, it's not that.
30.
3 goes into 23 7 times, right? With 2 left over. 3 goes into 21. 77. Okay, so what are the other two integers then? 7 and 11. Right? Okay, what's the trick though? If I gave you one of the numbers, I know that because q is 77, that's going to break up into 7 times 11. So that allows me to write this whole thing as in factored form, right? I could have written p as 3/7 times 7 times 11. Given 1, I could have divided the original number by that factor to get me the product of the other two. How does that help here?
Divided by factored parts, x minus 1.
So x minus 1 has to be, there's the key, right? If 1 is a 0, then what's the factor that goes with that? Yeah, so we know if this is true, then x minus 1 is a factor, right? Okay, and so we could write this if we wanted to. I can't remember what I put here. I think this is. Yeah, so I could write this as f of x equals x minus 1 times some other factor. How big's the other factor going to be?
3.
I mean, if I'm multiplying x minus 1 times another factor to get back that,
It's going to be
what? How much bigger? What's going to be the biggest power of x? X squared, right? So it's going to be quadratic, isn't it? So let's just call it q of x for quadratic. We just got to figure out what that is, right? So, well, we would do that by just dividing, wouldn't we? Right? Because I know this whole thing is equal to that, right? That's f of x. So couldn't I just do this? Couldn't I just say my original function, f of x, divided by x minus 1 would just give me q of x, right? Does that make sense? Okay. What's going to be the remainder? It's got to be 0 because it's a factor, doesn't it? Right? Can you make that connection too? You know that the remainder is going to be 0 because the value of the function at 1 is 0, right? There can't be a remainder if it's a factor, so we don't even need that there. I just wanted to make that point, right? Okay.
So, leave buffers.
Okay. So that's what we get. We know that the original function equals x minus 1 times q of x. So we just need to figure out what q of x is. Well, we can do that. That's just synthetic division, right? That's no big deal. So if we do the synthetic division, what does this work out to be? Okay, so if I divide that out synthetically, what goes where?
1 on the left.
Okay, so 1 goes out front,
Inside the out
1, okay, and then let's get rid of that.
0.
Okay, so we drop down the 1. 1 times 1 is 1. Negative 1. Okay. And of course we get 0. We had to, right? Because it's a factor. Okay, so what's that tell us then? That q of x, right? When we divide this out, q of x is equal to that polynomial with no remainder. So that's 1 x squared minus 1x minus 6 plus 0 over x minus 2, right? So it's just, okay? Okay? So we just divide it out synthetically, no big deal. And we get, not bad. We get that, right? So now what? If I want to find the other zeros, what do I do? Yeah, I could write it like that, couldn't I? So I know now I've got it factored. So my original polynomial equals x minus 1 times, we figured out what the other factor is. Yeah, now that's easy. All I got to do is just set it equal to 0 and solve, right? So if I set this thing equal to 0, well, we already know 1, 0 is 1. Duh, we're given that one. We've got to find the other ones, right? So what's that factor into? What are my magic numbers? Okay, and we get x equals 1, x equals 3, x equals negative 2. So I found the other zeros, didn't I? Okay, get the idea. So what would my strategy be there? Divide by x plus 3, right? Synthetically, and whatever I get back, if I know that that's a 0, I could do this pretty quick. If I know that that's a 0, then I know that I'm gonna get no remainder. So I could just go, whoops, I'll go negative 3, 1, 7, negative 33, negative 135. I already know I'm getting a 0 there. If I don't, I did something wrong. I divide it out. So 1 times negative 3 is negative 3. It gives me a 4 times negative 3 is negative 12. So what's that? Negative 45, 135. And then all I've got to do is factor that. And I don't even really have to write it out as a quadratic, do I? Because I know that that's just A, B, and C, so I can just find my magic numbers right from those coefficients, right? I can just go right from there if I wanted to. And factor that into, what would magic numbers be that multiply to negative 45 and add to 4?
5 and 9.
There you go. So positive 9, negative 5. And so I'd get my other zeros right there, wouldn't I? Negative 9, x equals 5. Okay. So here's the other kind of question. I'll probably give you something like this. Determine whether this is a factor of that polynomial. And if it is, find the others. And if it's not, just say no. N for no. How would I check?
Synthetically divide C to get 0.
Okay, good. I would just plug this, I'd run this through synthetically. I'd put a negative 6 out front. Everybody see that? Because I want the 0 of that factor, right? You want to know, is that a factor? So we would set it up where I've got a negative 6 out front, a negative 3, a negative 39, a negative 162, a negative 216. And the question is, what goes in there? If it's a 0, yeah, it's a factor, and I keep going. If it's not a factor. Okay? Okay, I'm going to make up one more for you. Let me show you one other thing I forgot to do. This is kind of cool. So, let's see.
You go back like the page.
No, it's not.
It's there's a couple.
Ever since I saw you do that, I did that.
Right there?
Yes.
Tabasco, and you slam it back, like you're doing hot sauce, like eggs, put them on the table. Tabasco, biscuits and gravy.
Like eggs. Three things. Yeah. Wait, what are we like?
I'm still logged into that computer. Probably should log out.
And go now.
Okay, I got a doozy for you. How about this one? So,
Oh, and I watched that one the other day. Like I watched yours, and I watched your guys', and I was all excited.
How many videos? What's your eyes?
So you guys have one, and you guys have one. Yeah, I think there's 6. Or maybe 7, because you guys have 2 chapters. Yeah, it'd be 7, because we would have 2 chapters, right? Yeah, but we didn't do the next one.
I like yours.
Yeah, it's fun. I don't remember actually. Was it, I didn't check. No, I didn't. Yeah. Do you remember? I just something about they were trying to sell that. Could you, like, yeah, I don't know.
okay, there's your challenge right there. How about that one? So I gave you this big, gave you a quartic polynomial. So a quadratic polynomial means it's the degree of polynomial is 2, cubic means 3. This we call this a quartic because it's a 4th degree polynomial. And I gave you a quadratic factor. I want you to find all of the factors. Factor this thing completely, let's say. Okay, what can we do?
Like by ourselves,
What's that?
by ourselves,
No, we'll do it together. But I just want you to,
to try.
well, let's just talk through it. No, we don't have time probably to do it on our own. What do you think?
Factor has magic numbers, so you can
okay.
factor it and then divide the bigger one by both its factors.
Okay, so we got a couple options. We got a couple options. So one thing, so Seth saw something good. So one thing we could do is we could just divide, option A would be to divide f of x.
By the factors of its factor.
Oops.
Wish we had copy and paste.
I know, I'm gonna be copying and pasting next time.
Some don't have beyond.
That is true.
Okay, one thing we could do, listen please. So one thing we could do is we could divide this by the whole quadratic factor.
That becomes tough.
Now we have to do one.
But you'd have to do long division, right? If we did that, that would require, which you know how to do, but it's kind of a hassle, right? Okay, but Seth saw something good here. He saw that the quadratic factor on the bottom is factorable. It splits into a product of 2 simple linear factors, right? So we could also do this. We could divide the whole thing by what's it factor into?
X plus 7.
Okay, x plus 7 times x minus 5.
Could you use the solution or just?
What do you mean?
It's like, -7, but.
So, okay, so dividing by two separate factors would be the same thing as dividing by one, and then getting the result and dividing by another, wouldn't it? Right, everybody see that? So we could also, if we wanted to, we could rewrite this as, it'd be really tricky here. Oops, not that tricky.
Oh, you missed the one. Never mind.
There we go. Okay, so that whole thing we could rewrite if we want to as everything on top, all divided by x minus 5. So the moral of the story is we could divide those sequentially, right? Now this is pretty cool. I'm going to show you a really good trick here. It's called nested synthetic division. I've never actually seen this done in a book, but I'm sure it's in books, but it works great.
Never actually seen it done.
Well, I mean, I'm sure tons of other people have thought of this too. It's not like this is such a great thing.
This has never been done before.
No, this is don't kid yourself. This has been done a ton of times. This isn't that big a deal.
Never seen it.
Oh yeah, cook this up in swag yesterday.
I mean, I've done this a ton of times. Okay, so here we go. Here we go. So let's do the top part first, right? Be with me, please. We're gonna run out of time. Here we go. So we're gonna synthetically divide out. What goes out front?
-7.
Negative 7. What are the coefficients?
10, -21, -509, 1281.
Seth, you're talking too fast.
Okay. Okay, what needs to go there? It's got to be 0, right? Because we know that's a factor. So it's got to be a 0 or we messed up. Okay, so what do we get if we do this? I get a 10. Okay. So what is that going to be? 637.
Aha, I was right about the -7 for 5.
And then what are we going to get here? So positive 128.
Yeah.
Oh boy, that's a biggie. So we're going to get 968, negative 968. Okay, what's that? So we're going to get 890. Say it again. This is 896.
Scrambled the first.
Yeah, I don't think we can.
It is?
Yeah.
Oh, you're right. 840. Yeah, 896. There we go.
You just had them switch block.
No, I messed up. 896. So if I add those, I'm gonna get
This is why we made.
385 times 7. Oh my goodness! Somebody just do that on here. I don't want to do that. Well, I know what it's gonna be. It should be negative 2695, right?
Yeah,
Did it? Oh, okay.
It is.
Okay. Okay, good. So it worked, right? We did it correctly, right? So now what? All we got to do, now watch this.
Divided by 5.
All we got to do is,
Add another bracket.
No!
right? So, I mean, I'm sure this has got to show up in a ton of textbooks. I just have, I mean, it's,
No.
I'm sure it does, I just haven't seen it, but it's got to be the
It's just the same thing.
It's gotta be.
It's just a convenient way to reuse the synthetic division stuff, right? You know, I might have even seen this, I don't remember, it's possible. So if I bring this down, 10 times 5 is 50, this should be an easier one. Negative 41, negative 205, and what's that gonna give us?
Negative
72 plus 4, 77, negative 77, and what do you know?
Really have to see negative 77 twice.
Okay, and so we get back to what we knew we were gonna have, right?
Okay, so is there a calculator?
Actually, you didn't know that. Okay, one more part of this though. There's another part. So we found what's left, right? We found the two zeros that were easy, right? Those were the easy ones because those are the zeros of that factor. Big deal. That was easy to find, but now we got to get the other two because there should be 4.
Where are those ones?
So how am I going to get the other zeros?
Quadratic.
Or how am I going to get the other factors, let's say? We wanted to factor this thing, what I told you to do, right? We wanted to write it in factored form.
Oh, magic number.
Oh.
So we've got the factors x plus 7 times x minus 5 so far, right?
Times.
So if we go back to this previous page, our goal was to write it in factored form. So we got this whole thing up here.
This is 1. My eyes are literally blank. My brain's
That's how that works.
Yeah.
Leaking brain.
That's gross.
Okay, so this equaled
blank.
x, was it x
Plus 7.
plus 7
Minus.
times x minus 5 times what, we got to figure out what else is there, right?
That thing we just got.
So we got to find the factors of that one. Now, we could. So we could go back and maybe try to do bottoms up, right? But I'm going to show you another trick here. I mean, it's not really showing you anything. You already have all the tools to do this, but I want to maybe tweak your thinking about this a little bit. If I set that up as a quadratic equation, you would instantly know what to do, right? If I set that up as a quadratic equation, 10x squared minus 41x minus 77 equals 0, how would you solve that one? Quadratic formula, right? So to solve that, we would just say x equals
Negative 3 plus 1 minus squared.
E squared
minus 4ac divided by 2.
I know that part. So what's 41 squared?
Calculator.
Hold on, I got it.
Calculator will tell us. What is that?
1,681.
1681 minus 4 times 10 is 40 times 77. So that one we can do 28, 28. That's going to be, yeah, 30.
Big numbers.
Plus though, right? Because we're multiplying by a negative. Okay, so that equals 41 over 20. Or actually, we'll just do it this way. We'll just say
I already wrote this.
41 plus or minus the square root of, what's that big thing? So that's going to be like 4, 7, 6, 1. No.
1,399.
What is it?
It would be the square root of negative 1,000.
Oh, no, that should be positive. That's positive, right? Because we're doing 4 times 10 times negative 77 makes it positive.
Oh, yeah, yeah.
4761.
Okay.
Okay, what is the square root of 4761?
Okay, hold on, I gotta unlock my phone for this.
23.
23. Oh, what do you know?
What do you know?
What? When did you get 23?
23.
Is it? No, it's not 23. What is it? What is it?
It's 69.
69.
Oh, yeah, 23.
So what's that give us? If we take the plus, what do we get? If I take the plus, I'm gonna get 110. Okay. If I take the plus, I get x equals 110 over 20, which is 11 halves, right? If I take the minus, just bear with me here, if I take the minus, I'm going to get negative 28 20ths. I can divide those by 4 and get negative 7 fifths, right?
Yeah.
Okay, so if I know those two things,
You can make those zeros.
aha, I could make those zeros, couldn't I?
Oh, yeah.
Whoa.
Oh, wait, there's more.
So there's my answer, right? If I have the answer, for example, x equals 11 halves, we now have a recipe. If that's a 0, what's the factor?
No.
Negative 11.
X minus 11 halves, right? Okay, now we would want to maybe, this is what's going to equal 0, right?
2x.
So why not multiply both sides by 2 and get 2x minus 11? You get the idea?
Do we go over that last part?
Yeah. Yeah.
Yeah.